Ok, bueno, vamos a continuar con nuestra siguiente plática. Next we have Todd. Thanks to be here, Todd. Todd is a principal engineer at Jack Pocket. He has, of course, a lot of experience using Elixir and know about the platform. And now we have the pleasure to hear about Liveview, and I think it's a talk more about the people, I think, something like that. So, welcome, Todd, and please.
Ok, gracias mi gente, gracias por darme la bienvenida a México. En los Estados Unidos, nosotros aprendemos español de España, no estudiar mexicanismos. So I'm learning mexicanismos while I'm here. So this is a term from, is it mexicanismo? What's up? Es que onda. ¿Sí? Okay. Okay, so, oh no, not good. Something's not good. What do you say? Chale. ¿Es bueno? Sí, okay. Viva Mexico. Okay. That's it for Spanish. Sorry. All right, so the talk is called The Phoenix Project, Liveview and the Theory of Constraints. The title might be familiar to you if you've read this book called The Phoenix Project. It's not a true story, but if you have read it, it sounds true. You've read it, right? You're like, oh, I know that guy Brent. Oh, I know this workflow, this sucks. Okay. So, but this project, this talk is about Elixir, Phoenix, and Liveview, and sort of applying the theory of constraints from those books. So the book they mention the most in the Phoenix Project is this book called The Goal. And this was the book that introduced the theory of constraints. It's mostly in manufacturing, but it can be applied to software development lifecycle, or at least that's what I'm going to try to do. And it was written by this guy, Eliyahu Goldratt, known for his drip game. Okay, that's an English term. His clothes, he looks good. Okay. But I'm also making reference to a couple other books, Accelerate by Nicole Forsgren, Team Topologies. So this talk is about a real project. I'm going to change a little bit of the details. And so far we're, 20 slides in. I haven't showed any code yet. And the good news is there's only one slide that has code. So I'll let you look for it. So about the project. So this is about a website for a company, I'll call it Sports Unlimited Inc. It's greenfield work, so it's a brand new project, no existing code, no existing team, and we had our UI, our UX provided by a separate designer. And the goal of the project was to ease navigation and the speed of interaction. And I'll contrast it to a previous project that we had, and I'll just call that Project X. So Project X is not just one project, it's a combination of all the other projects that we worked on at this company. But they have so much in common, I'm just sort of putting them all into this thing I'll call Project X. So the team composition for Project X is usually 4 to 6 back-end developers, 3 to 6 front-end developers, and then some others like a product owner, a designer, an SRE. So this is what our team looks like. And so we looked at our previous project, Project X, and looked at the flow of everything. So how did the flow of work go in Project X? And generally, I'd say it goes like this. So you get your requirements, then you begin back-end work, then you build an API, and then an HTTP client, and then the UI work. So that's kind of how our work flowed through the system. So sometimes, I mean, one of the problems, one of the constraints is that the UI work doesn't start, so that front-end team, those 3 to 6 developers, aren't able to start working until the API and the HTTP interface are built. So they're waiting around for us to deliver code so that they can take the handoff and build the front-end code out of it. So in the book, the goal, they would talk about, in lean manufacturing, you would have these end-on handles. Has anybody seen these before? Okay, one person. The Toyota way, this is like in a car factory, you would have this handle. And so anytime you got stopped from work or something was going wrong, you would pull the cord, and then everyone would stop and they would fix this one thing. So we would all work on this system so that it was not blocking people from that point on. But in software, we don't have those. So what happens is we deliver all this stuff to the UI. The UI says, oh, hey, we need you to parse this date into the existing time zone before you give it to us on the API. Or we need this other bit of data in the API so that we can present it on the UI. So it goes all the way through the system, and then it goes all the way back to requirements. And so if you think of it like in a factory, like in a car factory, it's like you get all the way to the end where they're putting in the windshield, and then they say, oh, like this glass doesn't fit, we need you to rebuild the whole front end of the car, and it goes all the way to the back. So that's the Project X flow of things. The flow is the most observable, is one of the most observable ways to determine how well or how poorly any system is working. So ideally, work only moves in a single direction and at a predictable cadence. So in the goal, I mean, you would take a bird's eye view of this factory and you would look and you would just see things moving from station to station, and that gives you an idea. That's the flow of the factory. If things are stopping at one point for a while or they're moving backwards, then you would know that's a problem. Okay, so while we're looking at the flow, we also looked at where the constraints existed in that project. So the theory of constraints, which I mentioned is talked about in that book. The theory of constraints is a management paradigm that views any manageable system as being limited in achieving more of its goals by a very small number of constraints. There's always at least one constraint, and the theory of constraint uses a focusing process to identify the constraint and restructure the organization around it. Okay, so that's heavy talk, but if you look at this illustration, you'll see if these are all the steps in completing, step 2 has the lowest flow, so that's your bottleneck. And so you would identify that as saying this is the bottleneck in our system. And so what you apply to the theory of constraints is you first look at the system and you identify that constraint. So step 2 was the constraint. Then you exploit the constraint. This is so exploiting the constraint means looking at it, eliminating everything that doesn't provide value. Then you subordinate. So this is kind of counterintuitive, but you say everything that's after that part of the flow, you could just slow down on, because they're only going to be able to work as fast as step 2. So don't put as much work into step 3, step 4, and the finish, because they'll always be waiting for more work to come in. So you subordinate that, then you elevate the constraint. So that means applying more machines, more people to step 2 where the bottleneck occurs, and then go back to step 1. So once you've elevated the constraint, it shouldn't be your constraint anymore, and now one of those other 5 steps is going to be the slowest, and you just keep applying this over and over again. Okay, so how does this apply to the software development lifecycle? So for us, we found that our constraint was often that handoff between the back-end team and the front-end team. So we looked at it, the exploiting it. Are there any tasks that we're doing that aren't necessary? Is there anything that we're working on in the back end that's not providing value to the customer? And so we looked at all that stuff. Could we hand off things in smaller batches? Could we, maybe find some other way to build the system so that they're not waiting for us? And here, so maybe, so while we're subordinating, we say, okay, well, maybe have the backend developers work on tech debt, or maybe we'll bring over more resources to whatever is blocking that handoff to make things move faster. But then we thought again, what if we didn't have a handoff at all? And that's where this comes in. So Phoenix Liveview. Is anybody using Liveview yet? Yeah. Just clap. Okay. Okay, good. So we looked at Liveview. How could we apply Liveview to this flow, and how would that change things? So when using Liveview, the flow looks quite different. We've got requirements, then we've got back-end work, and then we've got UI work, and then that's it. We no longer have to create those APIs, those REST APIs, and the HTTP clients to kind of talk back and forth with the React team. And that also means when we get to the UI work, we have the same group of people that are saying, oh, crap, we need this number presented as a float. And it goes back to back-end work. So we're not moving all the way back in the process. It's the same team that's saying, we're working on the UI, okay, I'll change this in the back-end. So it's much easier to fix, not only because the same team is working on it, but also because you're already in the context. So you've been freshly working on that back-end code, and so you know where to make that change. All right, so implementation. How do we implement that? This gets complicated again. So we applied Conway's law. So it's not the Conway that you're thinking of Conway's game of life. But anytime you're proposing any kind of new architecture, you want to consider Conway's law. So we're talking about John Horton Conway. He is the guy that made Conway's game of life. That's the one you're probably thinking of, and big in game theory. But this Conway's law is Melvin Conway, and so he went to, he's a PhD of Case Western Reserve University. Go Spartans. Any Spartan? No? Okay. He's the guy that developed the concept of coroutines in 1958. So any C programmers use coroutines? No? Okay. It's too young of a crowd. Okay. Ask your parents, and then they'll say, oh, coroutines, yes, C, that's awesome. Okay, and incidentally, he also worked on the spec for mumps and published the mumps manual. Anybody did any mumps programming here? Has anybody heard of mumps? Mackenzie has. Okay, it's a weird system that's used in hospitals and finance, and I think that's it. It's developed at the Massachusetts General Hospital Utility Multi-Programming System. Okay, so if you want to make a lot of money right now, become a mumps programmer, because there's a lot of software out there and there's not a lot of people doing it. Okay, all right, so here's Conway's law. So any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. So this is huge. So I'll give you an example. So if you have 4 teams working on a compiler, what you're going to end up with is a 4-pass compiler. So your architecture is always going to end up reflecting the way you have your teams organized. Unfortunately, for a lot of us, our teams are being organized by management, maybe HR, okay? And so if they're deciding on who's getting hired where, what the teams look like, effectively, they're sort of designing your architecture for your system. And that's bad. So here's an example. So if you've got 4 front-end teams, 4 back-end teams, this is common. And then let's say you have 1 database administrator and 1 SRE. What you're going to end up with, most likely, is this monolithic database. So all the applications talk to this same database. All the applications use this same infrastructure because these 4 groups, these 4 teams are funneling into one resource. And so when you have found yourself with an architecture you don't like, you can pull this inverse Conway maneuver. So what this does is it basically says your first draft of your architecture is your team organization. So the inverse Conway maneuver says this is how we designed our architecture. So first thing we want to do is make our teams reflect that. So if our teams reflect that structure, then our architecture is going to turn out the way we want it to. So that would end up looking like this. So we reorganize our teams. Now we have 4 people working on the database, 4 people working in SRE, 4 backend, 4 front-end teams, and now that reflects the architecture where we want, that has a series of services rather than everything funneling into this monolithic database. So for how this applies to Project Phoenix is we would have a backend team, a database team, and an SRE. So we remove the front-end group from that project completely, and having the backend team do all the front-end, all the UI, all the Liveview interactive components and everything. So that eliminates, or this team structure will give us the architecture that we're looking for. So, pregunta. Won't that just put more work on the back-end team, and then won't the delivery time be the same? So it's a reasonable question. So if you say, well, there's this much work to do a front-end and a back-end, and then you just make these people do both, won't it just take twice as long to do? And the answer is not really. So that has to do with communication structures. So the team size matters. So larger teams require more communication structures, more meetings, more people talking to more people, more context to keep in mind. And you could apply Brooks's law to this. Brooks' law is an observation about software project management, according to which adding manpower to a late software project makes it later. And this was coined by Fred Brooks in the book Mythical Man Month. Some people are familiar with this. So this is the idea, like management puts more people on a project and they think if they put 9 women together, they can have a baby in 1 month. If you ever try to put 9 women in a room together, no, not a good idea. Oh no, I'm just kidding. So, but it won't work. So the idea is you add manpower and it just makes more meetings, more communication structure. It actually will make the project later. So under certain conditions, each person you add adds more time to the project. And that has to do with this combinatorial explosion. So that's the rapid growth of complexity of a problem due to how the combinatorics of the problem is affected by the input constraints and the bounds of the problem. And so visual. So this is what linear growth looks like on this chart. So complexity goes up linearly. Exponential growth, you see this curve. And then this is combinatorial explosion. So this is the complexity that happens as your team size grows. So another way to look at that is if you have a team of 5 people versus a team of 8 people, you can look at the communication structures. So in this case, I've got lines representing each person's communication with another person. And so a 5-member team, you have 10 total connections. On an 8-person team, now you have 28 connections. So that's the combinatorial graph. So if you add 9, 10, it just becomes super complex. Incidentally, in distributed systems, you have to look at this as well. So if you have, Mackenzie might be talking about this at next role, but if you have a lot of networked systems together and they have to know what each other are doing, you have the same sort of structure. If you're interested in that, I'd recommend a library called Partisan by Christopher Micklejohn that increases this efficiency. That's a different talk. Okay, so Dunbar's number. More rules we're applying to this. So this is the suggested cognitive limit to the number of people with whom one can maintain social relationships. The strongest form of communication happens in an individual team working closely together with a very consistent shared context and specific purpose. So in software, this number is supposed to be 8 people. At Amazon, Jeff Bezos describes this as the 2 pizza rule, which is your team size should be no larger than the number. Basically, you got to order 2 pizzas for your team. If you have to order 3 pizzas for your team, for them all to eat, that's too big. And so the teams working as a cohesive unit perform far better than collections of individuals. So I think we all know this is true. Like once you've worked with somebody for a while, you can work faster on things. You kind of know what each other are doing. So the problem is when you grow too big, the intimacy of those relationships starts to fall down. The trust starts to fall down. And so you don't have that anymore. You're kind of communicating around each other or over communicating to kind of compensate. So any growth beyond Dunbar's number imperils the viability of the software being built by the team because trust will begin to break down. So you want to keep the teams at 8 people, essentially. All right. Queuing theory. So we're looking at queuing theory to try to apply that to the software development lifecycle. And so this is another reason I think we could work faster with that smaller team. So queuing theory is a mathematical study of waiting lines or queues. Queuing theory has its origins in research by Agner Krarup Erlang, a name we probably are familiar with, when he created models to describe the system of the Copenhagen Telephone Exchange Company. So we have our history all the way back to this guy named Erlang who was building or developing the concept of queuing theory. And so the idea is like you have incoming traffic here, you've got some queue system, and then you've got service channels. So in software development, or in a more practical example, if you go to a store, you have customers, then you have a queue, and then you have cashiers. Little's law says the long-term average number, L, of customers in a stationary system is equal to the long-term average effective arrival rate, lambda multiplied by the average time, W, that the customer spends in the system. So expressed algebraically that way. And so if you imagine a small store that has 1 cash register, assume that everyone that enters the store will buy something. If the arrival rate becomes greater than the exit rate, the queue size eventually approaches infinity. So anybody ever use Sidekick? Does this ever happen to you? So your amount of jobs is increasing faster than the throughput of Sidekick or any background job processor. Eventually, you're going to reach infinity until it crashes. And so we're applying that to the software development lifecycle this way. So in our case, we've got Jira tickets, then we've got our sprint commitment, and then we've got our developers. And so for us, the bottleneck is right there, is moving from the sprint commitment into our developers. And the Jira tickets sometimes arrive faster than they can be completed, and then that's when our backlog reaches infinity. So if in Project X, this would be really what the queue looks like. So we've got Jira tickets. We've got a commitment to back-end developers. Then the back-end developers create more Jira tickets for the APIs. And then we've got another sprint commitment, and then we've got front-end developers. So it's a very long line, and now we've got 2 bottlenecks in the system. And anytime there's errors, they may not be discovered until very late in the process, and we've got to go back to the first line again. So in the case of Project X, we identified this as our bottleneck, which was the handoff between the back end and the front end. And that's why in the Phoenix project, we moved to this. So got rid of the back end to front end handoff, just had everybody work on everything. And so now we've removed the bottleneck and we have this flow. Another issue that slowed us down, I think, on Project X was the complexity of things. So the cognitive load of having this big system that's in Elixir and Erlang on this side, and Postgres, as well as React and Tailwind, or whatever other front-end libraries might be used. So it creates a big cognitive load. And so, I mean, this one, cognitive load, no one is immune to that. This is just part of being a human, is that you have an inherent load that you can, of working memory that you can use. And so we break it down into three parts. There's this intrinsic load, which is the inherent difficulty of the subject. So you're working on a really complicated problem. That is called intrinsic load. You just have to think, grind through it. You've got a germane load, which is the part of your brain that's devoted to integrating new information, things that you're learning. And then you have the extraneous load, which is all the unrelated matters that still require attention. So meetings, production outages, whatever, so-and-so, has an interview today, et cetera, et cetera. So you've got this cognitive load. And so in a complex system that has JavaScript and CSS and Elixir and Erlang and whatever else in between, it becomes impossible to reason about the whole system. So eventually you get to a point where nobody understands how everything really works. And so reducing the amount of complexities in the system decreases that overall cognitive load. So in Project X, the cognitive load kind of looks like this. We've got a Phoenix app, and then we've got this API code, and then we've got these HTTP clients that interact with the API, and then you finally got this React app on the other side. So having that much code created a high cognitive load and just made the system more complex. So in a Liveview app, it looks like this. So we've taken all those steps and we've boiled it down to this Phoenix app and then Liveview code, which is also written in Elixir. So switching context is really easy. The feedback loops are smaller because the code is right next to each other. It's relatively the same. And then this is the slide that shows some code. Hopefully you can all read that. I'm sure you can. But this is some example of Liveview code. And one thing that I love about Liveview is when you look at it with the callbacks, it just looks like a gen server. So instead of learning React or whatever the front end library is and figuring out all the patterns of that, it's like, here's Liveview, and if you know how to use a gen server, you're basically going to know how to use this. The callbacks are relatively similar. So switching back and forth between the back-end Elixir code and the front-end Elixir code, it makes that a really easy context switch. So like the Liveview callbacks we have, handle call, handle cast, like these are handle info. These are all the same callbacks that we have in gen servers. So it's really easy to reason about for me, and so context switching becomes pretty much simple at that point. So some other advantages of switching to a Liveview app, I think easier contract testing and integration testing. So testing the entire system becomes really easy. You're doing that all in XUnit. You can run it all in the same CI. Contract testing between layers, there's fewer layers to go through, so that becomes easier to do. You've got more flexible resources, so everybody on your team can add a button, can add a database call, can work on a gen server. Everybody's working on everything. You don't need to hire JavaScript developers. I mean, it's hard to hire anybody, so JavaScript developers are no exclusion, so not having to look for a separate set of resources is, advantageous. So the disadvantages we found, there's little access to pre-built components. So this project is a couple years ago now, and there really wasn't the things that, now we have things like Daisy UI and Tailwind UI that help things a little bit, but in React, I feel like, you need a calendar picker that does this, this, this. Okay, whatever, download that from NPM. There's 50 of them that will do the thing you want. And in Liveview, we really don't have the same access to that. At the time we were working on it, there was lots of breaking changes to Liveview. So right now we're at 0.18. So we're still in a 0 release, which means that the contract isn't necessarily guaranteed. Although I think McCord and the rest of the Phoenix team have said that like 18 is going to be pretty close to what 1.0 will be. But even recently, I mean, we had all those changes to HEEX, like the template system that just came in, and or to like 17 and 18 were like some pretty big changes. And so you have to be able to be flexible to deal with that, like upgrading your library code. Might be required more often than if you used a more stable front-end library. So in synopsis, how did it end up? I mean, the good news is we were able to spin up a team really fast because we already had Elixir developers. The product met our requirements. So we had requirements for interaction, the speed of interaction of things. Our customers were happy with it. And the design ended up pretty well by reusing some Liveview components and getting some help from Tailwind CSS, and then later on using Surface UI to have reusable components. So yeah, I would say Project Phoenix was a success. And I think that's it. So muchas gracias, BEAM Lite y Jackpocket. We're hiring. Again, come see one of us if you're interested. And I have got 6 minutes for preguntas.
Okay, so questions?
Thank you for your talk. It was very interesting. One thing that I have identified through the years is that a lot of backend developers don't want to write front-end code. They avoid it the most they can, me included. So not all of them, of course, but how did that work for you, and what do you expect in the future for situations like that? And if you have some tips for that kind of constraint for going forward with Liveview.
Okay, good question. So we had 3 back-end developers working on this project. And so myself, I started out as a front-end, I started out as a designer and then a front-end developer. So I was okay with it, as well as one of my other colleagues. The third one was definitely what you're describing. Was very apprehensive about going into front-end, building any sort of front-end. And I think the support that we gave each other was helpful for him, and I think I would suspect most of us that don't want to do front end or UIs, it's not because we don't like it. It's probably because we're scared of it. There's all kinds of there previously was all kinds of weird browser issues and CSS issues, and it just seemed too foreign to us. There's just too many things to learn. I think the amount of things you need to learn to build a front end in Liveview is so much decreased that if you give somebody a little nudge that's an Elixir developer into Liveview, I think they'll be pretty excited at what they can create. Also, I think we leveraged Tailwind UI and Tailwind CSS a lot, which I think was also very helpful. I was like, it's not that hard to add a button. Like, it looks like back-end code. So, yeah, I don't think I've really ever run into anybody that's been in Elixir that was just like, no, I just never want to do Liveview. I think it's natural to be apprehensive because you're unfamiliar with it. But I think, yeah, I mean, for us it went well. Everybody was happy to sort of learn it. And I know a lot of back-end developers, when they make something that's interactive, in Liveview, and they can do it in an hour or two, it's just like, oh, cool, like I'm pretty cool. I can like do all that stuff these React developers are talking trash about, and I can do this myself now, so that's cool.
Okay, thank you.
More questions?
Hi, thank you so much. I really like the idea of that how your team is going to dictate your architecture, and you had this slide where at first you started with 4 backend, 4 frontend, 1 database, and another one which I forgot, and then you put 4 on each one of those. That is costly, right? how do you like manage the cost of having 4 engineers on all of those 4 parts, right? Is it more convenient because the project is gonna come out faster, or how do you like balance the cost of having more engineers so your architecture is looking better?
Okay, yeah, so let me pull up that slide and I'll show you. So that slide was just an example of, this was an example of if you want your architecture to have a decoupled database and decoupled infrastructure, this is how you'd want your teams to look. So another interesting thing that we did and that we're doing now, in fact, is moving a lot of database and SRE work into the same backend developers. And so, again, kind of removing those constraints. And so right now, like on our current team at Jackpocket, backend developers are responsible for a lot of infrastructure changes, as well as database administration stuff. And we have support teams that can help in the complexity of that. If you're interested in this, I would read that book, Team Topologies, because it explains this in a pretty simple way, in good detail, on how you'd want to build those teams to do that. So this was just like a very simple example of doing that. In Team Topologies, there's this concept of supporting teams, and so the picture looks a little different, but I can't explain it very well right now without a picture. And the answer to all your problems is money. And that's not just in programming. That's
Definitely. Thank you.
okay. Thanks.
More questions?
Thank you. So good, the conference. And what about the seniority of the developers? Do you think that we need a specific seniority to implement this kind of process? We need a specific level of seniority? What about, or what do you think?
I think the makeup of a team is always very complex. So if you have 3 senior developers and none of them are interested in learning front-end code, you're going to fail. If you have a senior developer and let's say 2 more junior developers who have experience in React and have done front-end code before, they're going to be excited because they're going to say, I can participate a lot on the Liveview side of things, and while you're kind of teaching me the gen server side of things. So I think the chemistry is just different. I don't think it's necessarily seniority. I think it has to do with what your previous experience is and then how open-minded you are to learning new things. I think anybody that's at any level that's worked with a gen server can work with Liveview. Comfortably, I should say. That's my opinion.
Hi. Okay. Well, regarding there's a say that said you cannot improve what you cannot measure. How did you measure the improvement on the team speed overall, the project X against this greenfield project?
Okay. Who invited project manager here? Okay, so there are a lot of ways. So the term of flow that I described is sort of the general sense, and I would say a project manager is a person that would observe the flow because they're seeing everything go through the system. For us, we use a product called Sleuth. I'm not sure if anybody's heard of it, but it's used to keep track of DORA metrics. So DORA metrics are these ideas that were introduced in Nicole Forsgren's book, Accelerate. And it basically has to do with your time of delivery, your failures in this rate of failures in the systems, mean time to recovery, et cetera. So that's a really good way to describe flow. So if anybody's interested in those of measuring how things are moving through the system, I would recommend looking at that book Accelerate, and then also specifically at the software called Sleuth. It'll give you a really good chart. And it basically is just like this guy, Eliyahu Goldratt, would go to the factory, kind of look from above and watch every station work. It's basically like that, but for software. It's just a really good, comprehensive overview of how things are moving through the system. Again, that costs money. Money will solve your problem. I'm also available for consulting.
Hola. My friend want to ask.
Oh,
What about when you have a team for a complicated subsystem team or a shared services team where you have different kind of priorities and different kind of dependencies with this kind of atomic flows and things? How did you manage the communication and the prioritization between the different things if you have centralized resources?
okay. So I think the question is you have central resources that work on many different services, microservices or just smaller services that do different things. Okay. I can tell you how we do it now. It didn't really apply to this project in particular. No, that will take like an hour, honestly. It's really, really hard to. So in team topologies, they also describe a way of splitting off teams, like knowing, say, when your cognitive load gets to this high, then like these people should only work on these three services, and these people should only work on these three services, for instance. Because once you have 6 separate microservices, no one's going to understand all of them. And so that's talked about in the book Team Topologies. To be honest with you, at Yak Pocket, we are constantly kind of evolving the way our teams are divided based on business needs, as well as code structure and the complexity. And then we also have services that need attention for a while and then become very stable and almost never need attention other than maybe the occasional on-call person if some infrastructure thing happens to it. So it's constantly evolving. The book Team Topologies is the book to read if you're interested in that. It will tell you everything that you need to know, that you should know. Okay, I think that's time.
Okay. Yes. So thank you, Todd.